Well, welcome to geometry, and we're looking at lesson 108, an introduction to coordinate space. This is space as opposed to plane. Okay, on a coordinate plane, you only have two dimensions, but in a coordinate space, you have three coordinates, 3D coordinate system. So we're going to go moving, we are moving into three dimensions. And that means that you're going to have an ordered triple. An ordered triple. That means we have X, Y, and Z numbers. We've done a lot with X and Y. Now we have X, Y, and Z. All right. Now they give you a couple of examples here. And let me see if there's anything I need to tell you before I get to that example, though. I'm pulling my book open here. Sorry, folks. Oh, come on, right page. Sorry, should have done this before. Okay, yeah, and they draw it out for you real nicely on page 698. You should be looking at your book for that, especially because I'm not going to do example one per se because it just didn't find it beneficial to take the time to try to do the graphics for it. You're looking at the coordinates of the corners of a cube. And if you look at it, you can tell how big it is. It has a side of 2, and of course, it's the cube. It's 2 in every direction, and so it's fairly straightforward to come up with the triples for it. So look at that one. I think you can handle it. And example number 2 is graphing, and you graph it looks kind of weird, very honestly. What they do, they're going to graph the point 3, 1, 5. And so they start with X, and they go out 3 on the X-axis. They go 1 in the Y-axis, and they come up with a dot. And because they're because of the three-dimensionalness, they're not quite 90 degrees, because in order to fake 3 dimensions on a flat page, they're not quite 90 degrees. And then you want to do 5 in the Z-axis. So you go up 5 in the Z-axis, and you go out from go out from 5 on the Z-axis, out the X-axis till you get to the dot. Then you scoot over to the dot, to the spot directly above where the other one was. It's a little bit of art more than it is science. So that should make some of you really happy. Now, if you're doing a line in 3 dimensions, they do it like this. And there's something called the direction vector, which tells you how far you go from point A to point B. I think that's more or less your slope. This is kind of an interesting one. So then you have any point on the line, and if you have any point on the line and you multiply the distance vector by any t, and t does not have to be an integer, it could be any fraction as well, that would get you any other point on the line. Okay, so you have this is your y equals mx plus b kind of thing, except that you have x, y, and z instead of just y, and your b is in 3 dimensions, x0, y0, z0, and your slope is actually 3-dimensional also, d1, d2, d3, and then your x from y equals mx plus b is actually the t. So the t tells you how far you're going along that slope. The d1, d2, d3, the direction vector, that's a slope, effectively. Okay, let's see how this works. They start out by giving us 2 points. And if you subtract those 2 points, you get the distance vector, because you get the distance. Now, it's not the actual, it's not a single unit distance. It's a 3-dimensional distance vector. And I did the opposite of the book, as far as which ones I subtracted. So if you're following along, you're going to see that the signs are different, but otherwise we're going to be in good shape. So the distance vector is -1, -1, -5. 3 minus 4 is -1. 5 minus 6 is -1. 7 minus 12 is -5. You're doing x, y, and z separately. You're doing that also here with then finding 2 points. They ask us to find 2 points on the line. So now we've got this equation, our basic equation, x, y, z equals 3, 5, 7. That's one of the points. We're using that as our basic point. And then t times, and then the direction vector. And so if we plug in t equals 1, then you'd have -1, -1, -5. And then again, we add the x's, add the y's, and add the z's. So you get 3 minus 1 is 2, 5 minus 1 is 4, 7 minus 5 is 2. If t is 2, then you multiply everything by 2. So you have -2, -2, -10. 3 minus 2 is 1. 5 minus 2 is 3. 7 minus 5 is -3. So that's 2 more points in the line. And you could plug in any other t you wanted to and get more points on this three-dimensional line. Okay? All right. Example 4, we've got a starting point, and we've got 2 electrons moving to 2 different points. And the question is this a collinear path? Are they all moving on the same line? So the first thing we need to do is to find the direction vector. So we took the first electron, 9, negative 4, 6, and we get a direction vector, which would be 4, negative 3, 6. No, 2, excuse me. 2, looking at the wrong thing there. And then we put on our equation, we use the starting point that they gave us, 5, negative 1, 4. That's our starting point. Our direction vector is the 4, negative 3, 2. And then we put in a t. Now, what we're going to do is plug in the second electron, and that's actually the x, y, z. Now we have an equation, and what we want to do is see if that t works. If the t in each dimension is the same, then they are on the same line. If the t is different for each one, then it's not the same line. Okay? So if they have the same slope, basically you're solving for the slope in each dimension. And if all the slopes in each dimension match what it's supposed to be for this problem, then we're in good shape. So solve for t in each dimension. So 13 equals 5 plus 4t. Negative 7 equals negative 1 minus 3t. And 8 equals 4 plus 2t. See, we're doing the x on the first point is 13. X on the other side of the equal sign is 5. And the x part of the distance vector is 4. So that's 4t. Y is negative 7, negative 1, negative 3. Z is 8, 4, and 2. And if you solve each of those for t, you get 2. So that means they are all in the same line, and they are all collinear. All right, I think it's a little bit mind stretching, but hopefully you got that. So good luck on your homework today.